which is exponential growth and decay, Newton's law of cooling, and logistical growth and decay. By the way, for those of you going to be taking 212, a lot of our applications end up being logistical or exponential, but particularly logistical. They're pains. It's a pain as a formula, as you'll see when we get there. It's just a pain. Exponential growth and decay, we've seen that, by the way, when we've done the compound interest. That's where the compound interest formula comes from. And now we're going to be looking at decay. That's the old idea of radioactive materials, or when you've got stuff that's dying at a particular rate. Population, that's going to be growth. And it's going to be A is equal to A0 e to the kt, where A0 is the original amount, so essentially this is where we start. T is time. Could be time in seconds, could be time in minutes, it could be time in years, could be time in decades, but it's time, it's some increment of time. And K is the constant of uninhibited growth. And if it's growing, it's positive, it's decaying, K is negative. K is also something else. It says it's the constant, but it really is going to end up being the percent of growth or decay. And essentially it's a rate. It says how fast something is growing, how fast something is decaying. So for us, K is going to be a how fast. That's going to be your rate. And if we've got growth, this is what it's going to look like. It's A of t equals A0 e to the kt. K is positive, so this would be growth, and that should make sense. It's going to look like that. And the same formula, only K is negative, that's going to be decay. So growth and decay. So those are going to be for exponentials, the big guns. We're not going to do the data, that's 4-9, but we can actually come up with these formulas. Putting in data, we've got an exponential regression on our calculator.